Hi, my name is Iqbal Khan, and I'm a technology evangelist at Alachisoft. Today, I'm going to talk about NCache architecture. NCache is an in-memory distributed store for .NET and Java applications. It is extremely fast and scalable, and you can use it in your high transaction server applications to boost your application performance and scalability. There are two common ways NCache is used. Number one is as a distributed cache, um, where you cache the application data to reduce those expensive database trips. And number two is a messaging and streams platform. I'll go over both of those briefly before I go into the architecture. So in distributed cache, the application data caching means that you use an NCache API usually to just cache your application data, so you don't have to go to the database as frequently because cache is much faster than the database. It's also more scalable because it's in memory, so it's fast. It's close to your application, so it's fast, and it's distributed, so it's scalable. And if you are using, if you have a .NET application and you're using EF Core, then you can use NCache through EF Core as well, and also NHibernate and EF6 as well. If you have Java applications, you can use NCache as a Hibernate second level cache. You can also use as a Spring cache, or you can program against JCache. If you have the second part of the distributed cache use is if you have web applications that you can store your sessions in NCache, and then NCache replicates these sessions to multiple servers, so that if there's any one NCache server that goes down, that you don't lose any data. But these sessions are very, again, scalable because it's a very distributed store and it's obviously super fast. You can have there's also a multi-site session feature available in all the languages, .NET, Java, Node.js, etc. Um, in addition to sessions, for example, for .NET 6, ASP.NET Core applications can store their response cache in NCache, and they can also use NCache as the backplane for SignalR. SignalR is for live web applications where the web app has to uh, uh, send events to the clients. Um, so, and then if you're using .NET 4.8, you can also store your session state, view state, output cache, and also SignalR. Let me quickly show you what NCache looks like. Here's what it is as a distributed cache for mission critical applications. I use the word mission critical because in most cases, we see that our customers use NCache in very sensitive applications that are customer facing, and they are very important for their business. So NCache is part of your very critical infrastructure in that case. And these are, as I said, server applications that are high transaction. These are web applications. These are microservices, web APIs, or other server applications. Obviously, you can do .NET, Java, Node.js, or Python. And these applications are trying to access your database either as an SQL Server, Oracle, DB2, MySQL, or any other relational databases. Or they're accessing maybe your legacy mainframe data. Or maybe they are using a NoSQL database like MongoDB, Cosmos DB, Cassandra, or others. In this situation, NCache becomes a distributed cache by you use NCache as two or more servers as a separate caching tier. Although you don't have to have a separate caching tier, your application can run in the same box as NCache, and that just works perfectly fine. But the more popular deployment architecture is to have a separate caching tier. That's just a cleaner way to use NCache. So NCache, let's say you start out with a two-server cache cluster, NCache pools the memory, CPU, the network card resources of all these servers into one logical capacity. And let's say you're putting more transaction load through your applications onto NCache, and these two servers are maxed out. well, you can easily add a third server or a fourth server or a fifth server and so on and so forth. And Ncache never becomes a bottleneck. This is something you cannot do with your databases. Databases do not scale. NoSQL does scale, but in most cases, we found that people have to use relational databases in their for a variety of business reasons, and they also have legacy mainframe. So because the data storage layer does not scale, Ncache helps your application scale by letting you cache as much data as you can. The general goal is to have about 80% of the time you should find the data from Ncache rather than going to your database. If you can achieve that ratio, then you've taken the pressure off of the databases and your application is going to scale. The second common use case or use of Ncache is to use it as a messaging and streams platform, where you can have multiple applications that can communicate with each other through pub/sub messaging, through continuous query, or Ncache-based events. Let me show you what that looks like. So, for example, if you have a high transaction server application that need to do a lot of real-time messaging or stream processing, you can use Ncache. Now, the same Ncache that was a distributed cache now becomes a messaging and streams platform. Again, it's an in-memory distributed store. It scales linearly. It replicates the messages across multiple servers. In fact, Ncache also has persistence uh, in it. So with that, you can have different applications. For example, pub/sub messaging is a very popular way. It's a methodology. It's a paradigm where you have multiple publishers and multiple subscribers that can communicate with each other in a decoupled fashion. Decoupled mean the publisher does not know who the subscriber is. They just publish messages onto certain topics, and the subscribers can get them. Continuous queries in the same way. So those are the two common ways Ncache is used. Now let's talk about how Ncache handles .NET versus Java applications. Ncache has a very unique native multi-platform capability that you'll find very interesting. Let me go into that. So Ncache tries to provide you a native solution for both .NET and Java. And by that, I mean that when you have a .NET application, your entire application stack experiences .NET. You're not using anything but .NET. So for example, Ncache has a native .NET client, which is what your application is going to use on your application. This runs on your application server. And this, Ncache has developed this in C#, 100%. Similarly, if you have server-side code like read through, write behind, loader, refresher, that you have written in .NET, Ncache will run that code in its own .NET CLR process. Let me show you how, and I'll come back to this diagram back and forth. So for example, here's an NCache architecture. You have a .NET application here that may be running on Windows or Linux. It has a native Ncache .NET client, and this is talking to an Ncache cluster, which is a .NET Edition Ncache cluster. So that means that the server-side code is also .NET. Now, the way Ncache is architected, and this is what makes it really powerful for multi-platform native support, is that there's a cache process, there's a management process. Those are separate from your server-side code process. So, and there's a very high performance RPC. It's an in-memory RPC that Ncache uses. That Ncache has developed its own proprietary RPC, which is super fast. So that's how the cache talks to your server-side code. So for example, if it has to call the read-through handler, your read-through handler is going to be running inside this .NET CLR process to go to your database to get the data, and then it passes it to the cache. And the same thing goes for write-through, the loader, and the refresher. So you get the entire experience that your application has is .NET. Well, let's switch to the Java side. Again, on the same way, you have a Java server-side code, and Ncache has a 100% Java client that runs on your application server. And then the same way as .NET, here's the Java edition. Let's say you have a Java application that may be running on Linux, most likely, or maybe even Windows, maybe Docker, maybe Kubernetes. So that application will embed the Ncache Java client, which is, as I said, right here, 100% native Java. And then This Java client it's a grounds up identical to .NET client. It also talks to the cache cluster, the same NCache cluster, the same way that the .NET client does by using NCache's own proprietary socket protocol. And the NCache server is architected so that your server-side Java code is going to run its own JVM. So all of the development and testing and debugging that you will do will be all in native JVM processes. And this cache process will call your, let's say, read-through handler, which will go into, let's say, maybe your Oracle or DB2 or even SQL Server database, and get the data and give it to the cache process. Again, the same high performance in-memory RPC is used. So by having an architecture which kind of encapsulates the .NET and the Java code in their own native processes, NCache is able to give you a native stack for both Java and for both .NET. And again, in case of a Java application, you may want to do your development either on Windows or Mac OS, and NCache supports it completely, or even Linux. And then you're more likely to use Docker and Kubernetes than the .NET folks. NCache provides you the Docker images, and then also full support for Kubernetes, the Azure AKS, the AWS EKS, the Google GKE, or the Red Hat OpenShift. You can very use it in a very seamless fashion. So NCache is very unique in that it gives you a native .NET experience and at the same time a native Java experience. So if you're a Java shop, you don't feel like you're using a non-Java product. And if you're a .NET shop, you don't feel like you're using a non-.NET product. That's the beauty of NCache, the way it's architected. Okay, let's now get into the dynamic clustering part of NCache architecture, which is for high availability. And just one second. Okay. So the first part is the dynamic cluster. When I use the word cluster, I do not mean Kubernetes cluster or any other operating system level cluster. This is NCache's own TCP-based cluster. And this cluster has a peer-to-peer architecture. What peer-to-peer means is there's no master, there's no slave. Master-slave has problems that if the master goes down, the slave either becomes inoperative or becomes limited. Whereas in a peer-to-peer architecture, every node is equally capable. There is obviously a cluster coordinator node, which is the oldest node. And then if that node ever goes down, the next oldest is automatically selected as the cluster coordinator. The cluster coordinator does cluster membership. It manages the distribution map, the cluster health, and a bunch of other things that I'll go over some of that. The dynamic clustering means that you can add or remove servers to the cluster at runtime without stopping the cache or your application. There's no interruption. And let's say if you add a new server to the cluster membership is obviously updated at runtime. And that runtime information is then propagated to the clients. And I'll talk about that in the next slide a little bit more. There's also a cluster connection failover feature. So because these are sockets, although the cluster servers usually are in the same subnet, fairly close to each other, but that may not always be the case. We do have customers that have servers even deployed in different regions, and it works perfectly fine. Although we recommend that in most cases, the NCache servers should be fairly close to each other. But there could still be connection failure. If that is the case, NCache has a retries logic, and there are timeouts. There's heartbeat logic. All of that is to make sure it's all dynamic. The other part of the dynamic architecture is the dynamic clients. So just like the cluster had the ability to add or remove servers at runtime, you also have the ability to add or remove clients at runtime. What does a client mean? A client is the NCache client that runs on your application server, your web server. That's the part that your application talks to. So you can add a client at runtime, you can remove a client at runtime without stopping NCache, the cache, or your application without having any interruption. So that's the first part. The second part is the dynamic configuration. So as I mentioned in the last slide, when you add a server to the cluster membership changes. Well, that gets propagated to all the existing clients that are connected. so that they now know that there's a new server that they need to connect to. So if they choose to, based on the caching topology, they may connect to that server as well. Additionally, depending on topology, there may be a distribution map. Distribution map is more for partition cache and partition replica cache, but that also, as you add a server, it gets updated and that gets propagated at runtime. And also a bunch of other configuration changes that there's a hot apply feature that you can do, and that gets propagated at runtime. So that's the second part. The third part is that, again, there's a client connection failover, which is the same way as the cluster connection failover, but this is actually needed even more because the clients will probably not be very close to the cluster servers always. And they're more like, it may even be some routers or firewalls in between. So the connection between the clients and the cluster is more likely to break. So NCache has fairly intelligent retry capability, timeouts. There's also keep alive capability so that the client stays connected. Even if the connection breaks, the client reconnects itself to the NCache cluster. Another important topic of dynamic aspect of NCache architecture is the split brain. The split brain is a phenomena that can occur in the cluster. And split brain occurs whenever, let's say if you have a healthy cluster of 6 servers, a split brain occurs when the connection between some of these servers breaks for some reason. And there's a lot of, anytime you have network connections, they can break. And we see that all the time. So when that happens, that subclusters are formed. Let's say in this case, there's a split 1, split 2, split 3. Each subcluster thinks it's the survivor. So it creates its own cluster coordinator and it's an independent cluster. However, the collective, all the servers in this cluster, all these splits, remember that they used to be part of a healthy cluster, and these servers did not leave willingly. They did not leave in a smooth fashion. You did not do a leave node from an NCache management tool. Instead, the connection broke. So they will keep looking for these servers to see if the network connection is restored. And most of the time, maybe 5-10 minutes, half an hour later, that connection will most likely be restored. When that happens, a split brain recovery is done. And that where these splits are merged, these subclusters are merged in an iterative fashion from largest to smallest. And there's some data loss, obviously, because these became independent clusters, and now some of the data has to be lost. But it's all done automatically based on the rules that you specify. There's more detail about the split brain in a separate video, but this kind of gives you an overview. It's a very important feature that ensures that your NCache cluster stays healthy and can recover whenever a split brain occurs. Okay, now let's move into caching topologies. Caching topologies are essentially data storage, replication strategies, and also the client connection strategies. There are 4 topologies. One is partition cache, partition replica, replicated cache, and mirrored cache. Let's go with partition cache. Partition cache is basically that the entire cache is broken up into partitions. Every server has one partition. And there are this concept of buckets. So every partition has buckets. That there's a total of 100 buckets for the entire cache. So depending on how many partitions you have, those buckets are evenly divided among them. And these partitions are created at runtime. That's the important part in this. So as you add a server, a partition is created. Let's say you start with one server, there's only one partition. All the 100 buckets are in that partition. If you add a second server at runtime, not only is the cluster membership information updated, which I mentioned in previous slides, but now a distribution map is also updated. A distribution map essentially is a map of which partition contains which buckets. So let's say if you added a second partition, the distribution map will now be changed. A distribution map is actually, it's a hash map mapping to buckets. The hash map value ranges to buckets. And this does not change based on how much data you've added. It changes only when you change the number of servers, the number of partitions, or you do the data rebalancing. So the partitions are dynamic. The second part is that there's dynamic data balancing. So because this is all hash map based, it is very possible that based on the type of keys you used, that some of the partitions, some of the buckets will get more data than others. And you will end up with some partitions almost being full and the others are almost empty. And when that happens, the NCache has this feature where you can set a threshold and say, let's say if a partition becomes more than 80% full, remove 20% of it, or 10% of it, or 5% of it. Or not remove, I mean, dynamically balance it out. So data balancing means taking those buckets from partition one and copying them to other, or moving them to other partitions. So data balancing ensures that the data and all partitions is fairly even. In partition cache, every client connects to all the partitions on all the servers. The reason it does that is because it wants to directly access whichever item it wants in one call. If it were only connected to one server, let's say, and it wanted item number 3, it would talk to server one will go to server 2 and get it. And that's a 2-hop operation, which is not as optimized as if the client could directly go where the data was. And the client knows that because of a distribution map. That's why the distribution map is created to help the clients know where the data is so they can directly go and get it from there. So partition cache has no replication. So if any server goes down, you lose that data. There's no way, except if you use persistence, which is I'm going to talk about in a bit, then even partition cache does not lose any data. The next topology is partition replica cache. This is our most popular topology, by the way, because it gives you best of both worlds. It gives you the partitioning, which is the scalability, and it also gives you replication, which is the high availability. So there's no data loss. So for example, it's the same way as partition cache. Everything is the same, but every partition now has a replica on a different server. So partition 1 is on server 1, then its replica is called replica 1, which is, let's say, in this case, on server 2. So just like the partitions were created dynamically at runtime, the replicas are also created at runtime when the partitions are added or removed. And they're obviously located always on a different server. The other part is that all the replicas are passive. Passive means no clients talk to them directly. The clients means these only talk to the partitions. And the partitions then update their replica. So whenever you update something in partition, the partition updates it in the replica. And that update by default is asynchronous. Asynchronous is so that it can be faster. First of all, the client does not have to wait for that replication to happen. Second, you can do a bulk replication. So you can combine hundreds or thousands of those updates together and move them or push them to the replica at once, because the cost of this network trip is much faster or much costlier than combining data. However, the async replication obviously has that it's not always consistent. It is eventually consistent, which is good enough for maybe 95 to 99% of the times. And there's maybe 1 to 5% of the cases where you are dealing with very sensitive data. So you don't want asynchronous replication, you want synchronous replication. So there's a feature called sync replication. You can turn that on. And when you do that, then whenever the client updates items in partition, that operation does not complete until the partition updates the replica first. So if that replication fails, the operation fails. So that's how you know that if the operation succeeded, the replication also succeeded. So that's a very important feature of this. And then finally, just like partition cache topology, there's also dynamic data balancing on the replicas as well. So when the partitions are dynamically data balanced, then the replicas have to match that, because the replicas are always an identical copy of the partition. So they will also go through a data balancing. Let's quickly now go through how dynamic partitioning really occurs. So let's say if you had a 2-server cluster and you had 6 items in it, and you wanted to add a 3rd server. And I'm not adding more data yet, because that's another use case. This is just how the data is it shifted to other partitions as you add another node. So let's say you add a node, so there's a third server now. So partition 3 is created. And, and partition 3 now gets data from partition 1 and partition 2. So, so it gets some data from 1, some from 2. So let's say it takes item number 3 from partition 1, item number 4 from partition 2, and becomes partition 3. Now that it became partition 3, its replica has to be on a different server. So let's say it gets put on server 1. So server 1 used to have replica 2. It gets converted into replica 3. And then replica 2 gets moved into server 3. So for example, now all the data, now replica 3 will contain 3, 4 instead of 4, 5, 6, and replica 2 will contain 5, 6. All of that is going to be done dynamically at runtime without your application seeing any interruption. The same thing happens backwards, that if a server goes down, let's say you had a 3-node, 3-partition NCache cluster, and let's server 3 went down. Either you brought it down or it went down. As soon as that happens, because partition 3 is no longer available, replica 3, as you can see, I changed its color, it becomes active. Normally, as I've said, replicas are not active, right? Only the partitions are active. But now this becomes a partition. But it's only temporary because you don't want to have 2 partitions on the same box and then no replica. So now this merges itself here with partition 1. So let's say item number 3 goes to partition 1, item number 4 goes to partition 2, and your situation like this here. And this replica 3 now becomes replica 2. So the same thing happens backwards, all at runtime, dynamic partitioning, very, very flexible, very dynamic. This dynamicness adds to the high availability power of NCache. Well, although that dynamic partitioning is very, very useful, very powerful, but there are some cases where you don't want to repartition. And one of those cases is scheduled maintenance. Let's say you are doing an operating system patch, and that patch is going to be bringing the server down for 5 minutes or 10 minutes. Well, you know that your entire cache cluster might have tens of gigabytes of data. So you don't want to repartition just for that 5 minutes and then repartition again when you bring that node back up. So you can turn on a scheduled maintenance feature of NCache, in which case, when you bring this node down, again, you have to bring it down through your management tool. It triggers things that this replica becomes active, but there's no repartitioning. So it stays as 2-server configuration with partition 1, replica 3, partition 2, replica 1, and this replica 3 is actually partition 3, which means it's active and it operates. Obviously, it's not high availability because although partition 1 is backed up here, partition 2 has no backup and replica 3 has no backup. So, but this is only temporary because you're only needing it for 5-10 minutes. So once this server comes back up, it goes back to the old state and becomes a replica again when this becomes a partition again. So that's how the scheduled maintenance feature of NCache works. The next topology is called a replicated cache. In this topology, you can have 2 or more servers where every server has an entire copy of the cache, and every server is active, which means every server has clients connected to it. But here, every client only connects to one server because that server has the entire cache, so it does not need to connect to 2 servers like partitioned or partition replica. This topology, all the reads are super fast because the entire cache is right there. But the updates have to be done synchronously because both of these are active servers. So the same item could be updated here and here simultaneously. And you obviously don't want to go into a data integrity issue. So it's done in a synchronous fashion where there's an indexing scheme. There's actually like a sequence number that is issued, and every item is updated in the same sequence. So that allows the updates to be done always in a correct fashion. However, the cost is that a synchronous update means that if you have a client that updates item number 1, this server will notify server 2 to update item number 1. when both servers have updated item number one successfully, only then the update is successful and the control goes back. So that means it's not as fast as partition or partition replica topology, but the operation is guaranteed to be, if that's a update succeeds, that means it's always done to all the servers. This topology is good for read-intensive operations. For a two-server cluster, even the writes are pretty fast, not as fast as partition replica, but reasonably fast for most situations. However, as you add more servers, that performance of updates drops. Actually, it becomes slower because more servers have to be updated synchronously. So this topology has its own uses. That's why we keep it. Many of our customers do use it in special situations. The fourth topology is called the mirrored cache. This is, again, a very specific topology. It's a two-node topology only. There's an active and a passive node. All the clients, and again, the active node has the entire copy of the entire cache, and a copy of the cache sits on the passive node. All the clients connect to the active node, and they update the active node for all the stuff, and the updates are asynchronously mirrored or replicated to the passive node. And that asynchronous means it's also pretty fast, just like partition replica. In this topology, if active node ever goes down, the passive node automatically becomes active, and all the clients automatically move to the passive or the newly active node. And that way, there's no downtime, there's no interruption. And that's called the auto failover support. That's what I meant by that. And then obviously, when the active node comes back up, this becomes active again. The same thing happens in reverse. So mirror topology also is very useful for specialized cases. It is not scalable beyond these two servers, but it's got its own use because of the fact that all the clients connect here, and then you can do a replica onto a different box. I mean, this could be used, for example, in case of disaster recovery situation, for example. Another very powerful feature of NCache is called live persistence. Live persistence is available for partition and partition replica topologies only. And it is live, which means as you update the cache at runtime, the persistence store is also updated immediately. The update to the persistence store is asynchronous, so it does not interfere with your application performance or NCache performance. So that's how your application can stay very fast. The persistence is done at bucket level. So there are 100 buckets that represent the entire cache that are kept in a NoSQL document store. It's a file-based store, so it's not a server-based store. It's not a NoSQL database server. It's a NoSQL document store that NCache uses. You can use it in a common location that is common to all the servers in the NCache cluster, and that way they can all rely on the same persistent store. What some of the benefits of this are, and the reason this feature is provided, number one, that whatever you are persisting, you can, for example, persist the entire cache, and the entire cache is always persisted. You can say that whatever you're updating in the cache is, with the difference of a few milliseconds, it's also kept in the persistent store. So you can take that and reload that into a different cache, or if all the servers were to go down, you can always restart them from the persistent stores. You don't lose any data except very, very small amount of data. Or maybe you want to take cache from one environment to the other, you can easily do that. The other benefit is that it actually adds more high availability to partition and partition replica topologies. Well, partition topology, and I'll go into that in here. So partition cache, as I mentioned earlier, does not have any replication. So if any server were to go down, you lose that partition, right? Well, if you have persistence on, then you don't, because a copy of that data is also being kept in these buckets. So if this server were to go down, the buckets in memory get reassigned, but obviously without data to other servers. And now those servers know that these are empty buckets whose data exist in the persistent store. So they will reload that data from the persistent store. So that's how you don't lose any data even if a server goes down, even though you're using partition cache. Well, And you have the same benefit as a partition replica, as partition cache. The benefit you'll get here is that you can use more memory. You can store more data in the cache, because here you have to allocate more memory for replica, which you don't have to allocate here, but you do have to allocate the persistent store. So that's the benefit in partition cache. There's also benefit in partition replica. And it's kind of interesting that although this is already giving you high availability, but if the high availability happens only if one server goes down at any one point in time. But let's say if two servers were to go down simultaneously, and without the persistence, even in partition replica, you would lose data, because there's only one copy of every partition, and if two servers were to go down, then you've lost more servers than you can afford to. Well, with persistence, you don't have any problem. You can just reload all of that data from the persistent store. Now, obviously, in both cases, you have to keep in mind that whenever you load data from persistent store, if you had 3 servers, now you have 2. Well, the data may be worth too big to fit in the 2 servers. So that may be another issue that you have to deal with, is to make sure that you have enough memory on these 2 remaining servers that it can accommodate the equivalent of all 3 servers. So that's the only limitation. Otherwise, persistence really adds value to both partition and partition replica cache. Okay, another very important feature of NCache is called client cache. It gives you an in-proc speed in a distributed store environment. So for example, you have a distributed NCache cluster, your application is running here. This is usually a cache on top of your database or whatever else you're doing. A client cache is usually used when you have a distributed cache scenario. And a client cache is a cache on top of this cache cluster, and it sits very close to your application. It sits on the application server or the NCache client box, and it can even be in-proc or out-proc, depending on your preference. An in-proc cache is super fast because it actually keeps the data in a deserialized object form on your heap. So it's like having that object on your heap. It can get faster than that. So an in-proc cache is super fast, but at the same time, the beauty is that it is synchronized with the cache cluster, with the NCache cluster. And the way it's synchronized is whatever is kept in the client cache, the cluster knows about it. So if something that was kept in this client cache, another client updates in the cluster notifies that client cache to go and update itself. And then that client cache updates itself asynchronously. Obviously, there's a few millisecond delay, but that's, as I said, eventual consistency is the model in most cases, and that's usually acceptable for 99% of the cases. If that is not acceptable, then NCache provides you, and the optimistic synchronization is the default, which is where there's a few millisecond delay, and there could be technically a situation where you have stale data, which is okay, as I said, 99% of the time. But let's say if it weren't okay, and your data was very sensitive, but you still wanted to use the client cache, then you could use a pessimistic synchronization capability where it makes sure that before your application fetches anything from the client cache checks only to see if there's a newer version of that data. That's a faster call than getting the data itself, because NCache then keeps the versioning information. And then if there's a newer version of that data, then the client cache fetches it. If not, then it'll just gives it back from the client cache. Client cache you can use without any code changes. It just plugs into your environment, and it is good for read-intensive situations, where you're doing a lot more reads. At least 5-to-1 ratio, 10-to-1 ratio is ideal. But when there's 1-to-1 ratio, let's say in case of web sessions, then client cache actually does not help at all. In fact, it's not recommended at all. Okay, another part of NCache is where NCache does WAN replication to handle multi-zone or multi-region deployment of your applications. So for example, you could have your application deployed on 2 different sites for DR, for disaster recovery. One is active, one is passive. And you've got this application and NCache running with it. And this is another, you have an application here which is not running. But you want to make sure that if this site were to ever go down, this will immediately be able to pick up the load. So you can put a bridge. A bridge is two-node cluster itself, which can be on the same boxes as the NCache main, or it could be separate dedicated one. It's up to you. And then whatever you update in this cache is asynchronously replicated across the WAN to the other cache. So that's the active passive. You can do the same thing with an active active. Let's say if you have a situation where even this site is active, well, you can do the same exact thing with an active active where both sides can update each other. In that case, there's also a situation where conflict may reside, may may arise, and when a conflict means that the same item, the same key is being updated on both sides simultaneously. If that happens, the bridge by default applies the last update wins logic. So whichever has the later timestamp, that update wins. But for example, if you wanted, you could also provide a conflict resolution handler, which is your .NET or Java code that the bridge will call, and that will actually, and it'll pass both copies of the data or the object to that resolution handler, and then you can analyze the content to determine which one is more correct, and then you say, okay, this update wins, and then that update gets applied to both sides. As long as that gets applied to both sides, then there's no conflict. There's also the NCache has the ability to give you 3 or more sites in an active active or active passive or some combination of those. So for example, you need at least one active, but then these could all be passive or these could all be active, or it could be a combination of active or passive. So, and again, the same way, when there's more than one active, this could be conflict resolution. Finally, containers have become really popular, Docker and Kubernetes. So NCache obviously supports them because they're more popular on the Java and Linux side than they are on .NET and Windows side yet, but I'm sure that's going to change, with time. So either way, NCache is fully capable of handling it in both environments. So for example, here's a typical Kubernetes deployment of NCache. Here's an NCache deployment. There's NCache got its own discovery service. These are pods that can scale, and then you have applications within Kubernetes cluster that are calling their NCache clients, and this could be either Azure AKS, AWS EKS, Google GKE, or Red Hat OpenShift. Red Hat OpenShift usually is either another cloud like AWS, Azure, or Google, or maybe another cloud, but NCache supports all of them. And these pods could be Linux, which is the case with more common so in Kubernetes than not, and NCache works perfectly fine. And the application can also be Linux or Java or Windows. So these could be either Linux or Windows, Linux or Windows. The same way the WAN replication kicks in also, that if you wanted to, let's say if you had, because of cloud, you can have multiple availability zones. You wanted to do multi-zone Kubernetes. So the way we recommend is you create one Kubernetes cluster, have 2 NCache deployments. These could be active active or active passive. And then the bridge can either sit completely here, or you can even have a bridge split where one pod is on this zone and one pod is on that zone. And then the replication happens asynchronously. I think that pretty much covers the topic today. Let me actually, I will strongly recommend that you come to our website and either take a look at NCache Playground, which is really a very quick and easy way from your browser to use a live running copy of NCache. And you can even get a 2-node NCache cluster with all the tools without any installation effort. Or if you are ready, just come here and register and download either NCache Enterprise for .NET Edition or NCache Enterprise for Java Edition. As I said, you can get either the tar.gz for Linux and tar. Or .msi, or you could also get the Docker. You could just pull a Docker image of NCache. That's the end of my presentation. Thank you very much.